Algebra online lecture videos. Today we're going to be talking about section 5.4, which is solving equations with rational expressions or rational terms. This is video 2 of this section. This video is going to be relatively short. It deals with proportions, a special type of rational expression or rational equation, I should say. And that's only when we have a fraction or a ratio equal to another fraction or ratio. Notice there's no addition or subtraction in here between these rational expressions or rational terms. What we're going to look at is a method called the cross product or cross multiplication. In the previous video we looked at, well, what's the LCD? If we use the LCD we can get the same results. And one thing about the LCD is it will work every time with the equations, but the method we're going to look at called cross product here only works with proportions. So make sure that when you're looking at it, you assess the problem and see, oh, I have a fraction or a ratio equal to another ratio. Now, what a ratio is, if you're not too familiar with it, is it basically says, if I were to read this in algebraic terminology, it is 1 is to 4 as 2 is to 8. Now, if we think about this in a real-world application, maybe we have one car, and for every one car, there are 4 tires. And we know that's a true statement. All cars have 4 tires, otherwise it's a tricycle or a motorbike or something else. So if we had 2 cars, we would then have 8 tires. So that's a true statement. For every one car, we have 4 tires, so for every 2 cars, we have 8 tires. If we use the LCD here, I can recognize the LCD to be 8. If I multiply this side by 8, I get 2. If I multiply this side by 8, I get 2. 2 equals 2, so this is a true proportion. The ratio holds true. Or, if I reduce this, I get 1/4. However you look at it, a proportion must be true. Something is to something else. Now, what we're going to look at is the cross product. Let's see if, since we've determined that this is a true statement, we're going to use the cross product. And the cross product is just defined as the denominator of one side times the numerator of the other, and the denominator of the other times the numerator of the first. So if we do this, we get 8 times 1 is 8, 4 times 2 is 8. This is a true proportion. They are equal to each other. Excuse me. So we can use this cross product to solve other proportions as well. Essentially, we could use our LCD and multiply both sides by 39, in this case, would be our LCD, and simplify it. We have our answer. Or we can use the cross product. So I'm going to say 39 times 1 is 39, 3 times x is 3x, and now we can go ahead and solve it. If I divide both sides by 3, I get 13 equals x. Now, always check your work. If I plug that in here, 13 over 39, maybe I want to reduce it or multiply both sides by 39 or whatever I want to do to check my work. I'll find out, yes, 13 39ths is 1/3. That's a true statement. All right, so let's look at an example where we can apply the cross product. We could also use the LCD. Like I said, the LCD method that we've seen in the last video will work for all equations containing terms that are rational. So, but here we're going to use this cross product. I'm going to multiply each side by the other's denominator. So 2 times 9 is 18. 4x times 6 is 24x. And now I can solve for x by dividing by 24. And I'm just going to write this one out. 18/24 equals x. Always reduce. Otherwise, you might lose some points on quizzes or tests. You've got to reduce your fractions in simplest form. I look at these two and I recognize that they both contain a factor of 6. This is 6 times 3. This is 6 times 4. Those factors of 6 can reduce to 1. And I'm left with 3/4 equals x. And now I'm going to check my answer because I notice an x in the denominator for one reason. And I want to make sure everything works out. Nothing is undefined or anything like that. So I put in 3/4 here. 4 times 3/4 is 3. 9 divided by 3 is 3. So this side is equal to 3 when I plug in 3/4. This here, maybe we recognized this sooner and said, hey, I could have reduced that right from the get-go. Well, then it wouldn't have been a proportion anymore, or we'd have to do something to make it a proportion. So let's just look at it. 6 over 2 is 3. So 3 equals 3. That's a true statement when x equals 3/4. So we know this works. Please check your work. All right, let's look at another example that may require a little bit more work to get this here. If we notice, these are binomials. So we know our polynomials. This is a binomial, that's a binomial. And it may look a little bit more complex because we have addition or subtraction or some other operation in there. But all we have to do is first assess it. I have a numerator and I have a denominator. This is nothing more than a fraction. This is 5/3 a rational number. It's just a fraction. We have a fraction equal to a fraction. So it is a proportion. Let's find the value of x that makes it a true proportion. Now I'm going to multiply this using the cross product. And what we have to realize is because this numerator contains more than just one term, it has two terms, we have to use distribution. So I'm going to write it out as 3 times that quantity, x plus 1, is equal to 5 times the quantity, x plus 2. And now we have to remember to clear those symbols by distributing. I get 3x plus 3, and over here I get 5x plus 10. Make sure we distribute to all the terms. Now, here, some students would say, well, let's get our x's on the left and get our numbers on the right, and that's fine. But as a rule of thumb, I like to always move the smaller value of x so that I have a positive coefficient, less chance to make maybe a sign error. So I'm going to subtract 3x because 3 is less than 5, and if I do that, I get 2x on that side, which means I have to move the numbers to the left side. I'm going to subtract 10 from both sides. And I get -7 equals 2 times x. Now I'm going to divide by 2 and simplify x equals -7 halves. Now if you write it one way or the other, it doesn't really matter if you get -7 halves equals x or x equals -7 halves. They mean the exact same thing. So I just rewrote it in this order. Now I'm going to check my work. And I'm going to check my work using a method that is good review from, I believe, section 5.2 video. If you want to go back and check that out, it's complex fractions. So let's plug this value in when we check our work. -7 halves plus 1 over -7 halves plus 2. We're just replacing x with -7 halves. This has to equal 5/3 in order for this to be a true proportion. Now, why I say this is good review for a section that we've already covered in whether you're taking online or in class, hopefully you've covered this. We can use 2 different methods to solve a complex fraction. And the first one is combine the numerator to a single fraction. Maybe I write this 1 is 2/2 or this is 4/2. Combine them to a single fraction and then multiply by the reciprocal of the bottom. Or I can use the other method that we had discussed in the videos, multiply everything by the LCD. Well, in this case, we have 2 in our denominator, that is our LCD. So I'm going to multiply the top by 2, and I get -7 plus 2 over -7 plus 4. I just multiply every term by the LCD 2. This still has to equal 5/3. Well, let's find out. -7 plus 2 is -5. -7 plus 4 is -3. Is -5 over -3 equal to 5/3? Well, a negative over a negative is a positive, so this is a true statement. I do know that this value will work. X equals -7 halves. Now let's see an example of an application to a proportion. Here we have similar triangles. The definition of a similar triangle is 2 different angles that have the same proportions. And we can actually use proportions to work with similar triangles. Essentially what a similar triangle is their corresponding sides are proportionate. Or their sides in one triangle are proportionate to the sides of the other triangle. So I'm actually going to set this up in 2 different ways. It's all in how you interpret it. If I say their sides are proportionate, I could say 3, this leg of my triangle, is proportionate to this leg of the other triangle. 3 is to 4.5. Now we're asked to find x, so if this leg is proportionate to that leg, then this leg is proportionate to that leg. So we're consistent. This side to that side, this side to that side. So we're being very consistent in how we set this up. Notice our triangles of 1, the sides from one of the triangles are our numerators, and the side from the other triangle are our denominators. Now if I go ahead to solve this, I can cross multiply x times 3 is 3x, and 4 times 4.5 or 4.5 would be 18. And then I can divide both sides by 3, x equals 6. Well, I could have set this up another way, as long as we're consistent. I could say, and let's put an or statement in here because we'll actually get the same result. I could say, well, 3, the leg of this triangle, is proportionate to this leg of the proportion. I could say 3 is to 4 as 4.5 is to x. Notice these are the similar legs, they're both on top. These are the similar legs, they're both in our denominator on the bottom of our fractions. Well, let's see if it holds true. X times 3, when I do my cross product, well, I did that before, right? X times 3, 3x. 4 times 4.5, well, you notice once I get to this point, I have the same equation, so I should get the same solution. So it doesn't matter which way you set it up, as long as you're consistent and say either this triangle is proportionate to this triangle, like we have here, the sides of that triangle are proportionate to the sides of this triangle, or we can say their proportionate sides have to be equally proportionate. So I had 3 over 4.5, 4 over x. So that's an application of where we can utilize proportions. In the next section, 5.5, we're going to look at more applications to rational equations, where we can set up a rational equation from some given real-world examples and solve it using these methods once we've done so. This has been section 5.4, video 2. Thank you for watching.